computer. All right, so for today, your class participation needs a password. But you have until Friday class time to do it. I'll give you the password halfway through at the end. Just remind me, Brett, give the password away. Hopefully you started homework 4. Who started and started looking at homework 4? You did? All right. Talked about those already. All right. Today's lecture, we're gonna discuss PID controller. I posted the slides late. I forgot to give you access. I did upload it, but I didn't give you access until probably half an hour ago. So you're looking for it. It wasn't there. I mean, it was, but you didn't have access to it. All right. So we discussed about robot control. Last class, we talked about like we overviewed or reviewed system control a little bit. What's an open loop, closed loop? What does feedback means? How to calculate the error of a system? So your class participation would be to find the error of a closed loop system. So the same system we used on Monday, but now it's closed loop. So the term will be a little bit different, but you'll be able to follow. If you understood how to calculate the error, you'll be able to follow that. Now, PID controller is one method that you can use for controlling your robot. Now, it's probably not the fanciest way, but it's the easiest way, because as we talked, the control law is easy, and you'll see today. It's just one expression for the control law. But before we jump into PID controller, let's take a look and discuss how do we control robots. We have two main methods or common method of controlling robots. We either use operational space or task space to control a robot, a Cartesian space that includes a vector that has the position and orientation of our end effector. And we know our end effector is in following a trajectory. It has to do a task in the space, so we want to control that. That's one method. You have different way of developing your control law. You could use potential field, which we will use that. Basically, how does the potential energy of your end effector changes as you get closer to the goal that you want to be. And the other method is using the dynamic equations that we developed and inverse kinematic, because inverse kinematic tells you if you have the position of your robot, you can tell how the joints are arranged, right? So you can control every time with respect to the position of the robot. The other way is joint space control. This is a vector that your control is a vector that includes translational and rotational position of every joint. So vectors that include this information about every single joint. And you control the joints and your end effector will end up in a specific position, right? So two different ways. Controlling joints itself or controlling where the end effector is, which will translate where the joints have to be, right? Since in manipulator dynamic or application, a manipulator application, you're usually performing a task, right? Let's say you have a grabber and grabs things. So since the task itself is important, you end up controlling that. We're just going to focus on that first method, the task control or operational control. But what if we wanted to use joint space, right? What if we wanted to control the joints? So this is straightforward, because let's say that we have a desired position and orientation of our end effector, right? If we use inverse kinematic, you're gonna know what our joints are gonna be. Now we have to control it, right? To make sure every joint actually goes where they're supposed to go. That's the control part. So we saw that we can model our system. We can have a controller for every joint and make sure that specific joint goes to that joint variable. So it's supposed to go 35 degrees. We'll tell you're supposed to go to 35. You control the DC motor or the linear actuator. You read that Q that comes out of that system, so you have a vector. Now, this is an open loop, right? How do we know where things are? What should we do? Close the loop. So, from things that we know, how do we check what's in the closed loop? So, we had some desired position, right, for an effector. We use inverse kinematic to find the joint variable. Now we actually have the system, bunch of DC motors on the joint, and we say that, hey, go to this value. There's a control inside, make sure it goes to this value. It gives us a vector that it may or may not be the joints that we expected, the values for the joint. Now we need to close the loop and make sure that, and check the error if there's any error. What method we can use on the back loop, feedback loop, to compare the joint values that we calculated with the desired position? What? Yes, but what is it? You're looking at the slide. That's not the slide. I mean, that's smart, but I want you to think about it. So this basically says that, okay, I have a bunch of joint variables, right? And I want to know if these joint variables will take me to that desired position. That's forward kinematic, right? So if I put forward kinematic in the closed loop, in the feedback loop, sorry, I can compare if these joint variable will give me that desired position. If not, then I move my joints slightly, right? And you remember that not every joint has the same effect on your robot. So the first joint that moves everything has more effect on your robot. So when you're controlling, this will get more, if you're scheduling for the gain, more gain goes to the first joint, and second, and third, and the last one. So that's the part that you have to tune. So there are different ways of tuning. Let's say for PID, the simplest. So the procedure will be, I have a delta X, a desired position. I know I can find that using Jacobian, right? So outside of singularity, so for joint space, making sure that we are not sending our robot to the singularity point. Delta theta will be Jacobian inverse of delta X. You know that there is another method using Jacobian transpose. If we use Jacobian transpose, you don't have to worry about the singularities, right? So finding delta theta from the Jacobian inverse times multiplied by delta X, we know that our arm will be initially at some theta position here, right? So we move here. So let's say it's initial position. We have values for all of our joints. Now, so X is F theta, delta X is XC minus X desired minus X that you currently are. We have delta theta, which is this Jacobian inverse delta X. We can find what is our next theta would be based on the initial theta, the initial configuration, plus this change, right? Now, every time you calculate that Q, which is all your thetas, send it forward kinematic, X minus X desired. That's what is here. You create this delta X, you go and find changes. So if you want to move everything by delta X, so this is a vector, right? How our delta theta should change. So once we have this, our next round of thetas come from here. So from this, you're using forward and inverse kinematic to control all the joints, right? Now the thing is, let's say we are using a PID controller. We can't use normal way of tuning, like what you were saying. You will end up using quasi control. You end up using a genetic algorithm, some of the adaptive algorithm, because there are so many joints, and you have, so everyone, so PID is 3 gains. Let's say you have 6 joints, 18 gains. You can't be doing one by one. You have to develop an intelligent method of tuning. But that's the part that you can't use the normal method of tuning PID controller. So all you do is for one DC motor. Now imagine you have 18 gains. So there are different intelligent methods that you will use here. So this is one way of doing it, right? And the procedure is very straightforward. Once you pick your controller, whatever method, then you have to tune it. If it's PID, we just talked about too many gains, but it is doable. There are other control methods as well you can use. Now so does this make sense, the procedure? Yes.
Why is the why is it tuning 18 parameters instead of just tuning like 3 parameters 6 different times?
So they all move together, right? So you have 6 DC with 6 joints. You have 6 DC motor, let's say, right? Now the first one has more effect on the robot. So when you're controlling this is going to move already in position of all of them. Then you have to tune the second one based on the first one. And that this goes. So you can't say, okay, let's just tune. You can't tune one by one, but it's like you have to recalculate everything and then go to the next one, go to the next one. Or you can have a vector and then develop an intelligent method to tune them together. All right. If your robot is simple, want to do it to the degree of freedom, yes, it's easy because you only have 2 elements, right? The first one is going to have more impact, and then the second one is directly connected to your end effect. So really depend on the configuration of your robot, you'll decide what method to use. We won't discuss tuning much because that's another universe and will take time, but I'll discuss the methods. So if you end up using them, for PID is usually like, if it's a simple system, it's trial and error. If it's a complicated system, then you have to use an algorithm. Usually available, you can just copy the codes. Genetic algorithm is one of them that is highly common. Now, let's say for a controller, we use PID, right? So we're going to discuss PID controller. So what is a PID controller? Those of you that had control before? Sorry. Yeah, what do you think PID controller does? So PID controller uses what? The error, right? Then you have 3 gains. You know, well, let's ask someone else. So what does the proportional gain mean? Like, what are we doing? Yes.
If try to extract the present here.
Yeah, don't look at there based on what you know, because that is, so I will talk about what that is, right? But if you work with PID controller, let's say, you don't understand what PI and D are, proportional integral derivatives, right? And you know that you're using the error of the system and trying to control that. Now, the proportional part, like, okay, I have an error of 10 centimeter. I was gonna go to 10, I went to 1. Every time I go, instead of going to 20, I'm going to 2. So there's a scale in my error. So if you say, get your signal, multiply by 10, you'll get where you're gonna go. That's it, that's your proportional. So P controller. Usually you just see as gain. So in the open loop example that we had, the blue box that had gain of 1/10, that's the P. So a lot of time you just say gain and you have gain in scheduling. So proportional is enough for your system, but depending on where you are in the operation of your system, you might have to change that gain. But can still be P, right? So then gain in scheduling can come from there. So that's the P part. A lot of times in the application of control, if the system is slow, P might be enough, right? So in designing PID controller, the less expression, let's say, no, not expression, hertz, PI and D. The less of them we use, the better, because it's cheaper, right? Then if you see that, okay, with just P, I can't get where I want to go, then you decide, Should I go PR or should I go PD? You don't go PID right away. All right, PID, because then you have to tune 3 things. And imagine times 6. If it was a 6, if you're afraid of the robot. Okay. All right. So now, PID controller, where the terms now come from? We discussed about P, but then to see that as we go, every time we add this 10 times or whatever gain, there is always a little bit more error. And as we go, we find that error accumulates, right? So it's the error in the past that goes over and adds up, goes to the present and future. So that's the integral part that we want to account for. So all the error that accumulates, we need to get rid of that. So we will use a coefficient, the integral coefficient, to basically account for those errors that were added up in the past. Then we also can understand or estimate our system's behavior and say, hey, if this has happened, I know in the future I might see this error, right? So that's where we have the derivative or the tangent of, if we, let's say here, you draw the behavior of our system, you will guess that there will be some error in the future which I can account for. And that's the last term, the derivative term PD. So the control law or the control signal for PID controller would be your K, or you can write KP, so it's consistent. KP times error. So KP, a coefficient that you have to tune, multiplied by the error directly. What's the error? Y, the output minus input, right? Plus KI term, which is the integral of the error in the past. So tau here, 0 to tau, what happened in the past. Plus your last term, KD, which is the derivative of the error. So here will be, for example, so y minus u divided by t2 minus t1, let's say. So this is the error term. And so because we will discretize, right, we will solve them at times. So you create a time vector. So you can check the error between every time. So you're reading from a vector. That's how you practice. If you are writing the code, you basically are using the error at each time step for your derivative. Now, this is the control law, super easy. We just need to remember this. You will read the error from our system. Either you simulate your system, either you are measuring the data, so the error comes from there. So that's not difficult. The hard part is, so what are KP, KR, and KD? How do I tune that? Right? We will talk about that, but this is basically in general your PID controller. Now, we usually go P. If P didn't work, we go PD. If not, we use PI or PID. Whenever you add integral term, you will see lots of oscillation in your system. Whenever you have lots of oscillation, you can add KD to the damping type of controller. It will damp your oscillation. If you have overshoot, you can use a KP to bring that maximum down and up, right? Undershoot or overshoot. So remember the shape of the second order system, right? So by looking at the response of your system, you can kind of guess what kind of control I'm going to use. And then from there, so this is for general any system. You look at the response, then you decide what kind of control I'm going to use, then you'll go for tuning. Any question on PID control itself? Yes.
I know that due to the derivative process, so how could you get the future?
So the future information, if you think about the tangent of, let's say you're on a path, right? So your next point will be along that tangent line. So that's why derivative. So y2 minus y1 divided by time. So if you have tau plus PD anytime in the future, because you're guessing, right? How your system is gonna behave. So that's why, like, in your PA3 for creating the trajectory, you make sure that the tangent of when you're hitting the points, right, they're aligned. So because the goal is so your system is not gonna behave something very different, right? So this is in general control law of PID controller, but for our purposes, we are gonna develop our control law. So I'm gonna show you how to do that, because so we know the dynamic of our systems, right? So we can use and we can take advantage of the dynamic that we know and the definition of our system to develop our PID controller. I'm gonna start from a very simple system. 1 degree of freedom robot, prismatic joint. Let's say you have a prismatic joint only, mass of M, and we want to know how can we control this robot to go from a position 0 to X desired, right? So what is the control problem? What is the control problem here? Yes, so we want to develop a controller, right? That we can always use that controller to go from any position for this prismatic to a specific desired, right? Do you remember that system that I draw, and what was the control problem? What are we actually trying to find? That's my question. What? The control law, where does it come from? So what am I looking for? There should be an input, right? I'm trying to control my input, because if I know what my input is, then I will always get to my desired. So let's say there is a force, that input, right? You'll use for reference input that is pulling that prismatic joint, and then we're gonna see how we can define a value or expression for that force, for input force. You want to make sure that you always end up at our desired position. We discussed mass spring systems, right? Briefly on Monday. Briefly. All right. So let's say this has a mass of M, and I'm gonna pull this with a force, so there's an input force, right? It creates an acceleration. So the dynamic, if you look at the dynamic of this system, we don't have any friction here. So do you remember mx double dot plus bx plus kx equal to 0, right? Mass spring system. We don't have a spring here. We don't have any damping. So the only thing we have is mx double dot. So in general mass spring system, mass spring damper. So we are modeling our prismatic joint. So in general is mx double dot plus bx dot plus kx equal to, let's say, some f. The only term we have here is just mass that's being accelerated by x double dot, and we want to make sure this f is in such a way that we will stop at x of b. So I'm going to use potential field approach for this. So this way you also become familiar with that method. So let's see what happens if we define a potential function So if this is X desired, once this mass starts moving, we're gonna have some kinetic energy, right? So the potential energy, wherever it was, whatever it was, there is a reserve potential energy in our system. Once the mass starts moving, let's say this direction, so this direction, so let's say this was x0, we started at x0. Our potential energy will will decrease, and then once we are here, the mass reaches at x desired. That's where we have to stop, right? That's where we expect our potential energy to be expended, all of it. But since we don't have any opposing motion, when we pull with the force, it will pass that point, right? We're just pulling, we're not stopping. We haven't defined anything that this will stop. So my potential energy, my kinetic energy goes back up. Well, my kinetic slows down, my potential will go up. So meaning that I pull this, it might have been too much force, it goes and stops here. Right? It passes the X desired. We are writing a general formula. So we don't know what exactly F is to stop at our X desired. We pull, some input, it crossed the position that we expected to stop, it didn't, and it stopped at some random position. Right? Does that make sense? Input, you pulled it, let's say this was here, I'm the prismatic joint, I was supposed to stop at this location. I'm not controlling it yet, right? So I just know there's a force. I pulled it crossed here, right? So I know that I need a force that has to pull it. So I'm going to develop that first, and then I'm going to add an expression that will make sure that it stops where I need it. Now it's control. Okay. So if I say based on this, Vx, my potential energy is greater than 0 where I'm not at X desired. This is 0 when I'm at X desired. Just the definition. Now, for this system, I can define potential energy to be 1 kp x minus x desired squared. Why am I doing that? So the reason is, since we are pulling, and then you say, oh, I'm not where I needed to be, I go back. Then I pull back again, then I go back. What does this simulate? Spring, right? So you're writing a potential and you're modeling this behavior as a spring. So that's the potential energy of the spring. So it keeps going between X and X desired. So what do you expect? You want to drive this X minus X to 0. Then you will stop, right? So there is no actual spring in the system, just the behavior. The way that the potential energy is behaving is like in a spring. Go back and forth because it wants to stop eventually at X desired. So for the potential energy and the potential field, your force will be negative gradient of your Vx, which is negative partial of V with respect to X. So that might be a new definition for you. So we're using potential field definition. So what are the changes of my system with respect to the variable I'm trying to control? Maybe green was not a good idea. It's very bright. It's not as bright on my iPad, I'm sorry. All right, so this is F, right? I define, I haven't defined it yet. So to create that F, so my F will be one half kp x minus x desired squared. So, which is negative So 2 and 1/2 cancel, KP x minus x desired. Right? So that is that's the control force, the control law until now. I know I have it in my dynamic equation is mx double dot equal F. F is the external forces, right? The force that is going to control is also an external force. So I'm going to now say mx double dot then is equal to negative kp x minus x desired. So there are two different things going on here. What is white? This is from the dynamic of my system. What's going on actually in the dynamic system? Now, you know how to develop the dynamic of the system based on how complicated your system is, right? This is the dynamic. This is a artificial force that you're creating because you want to control this. You want to eventually start at x of d, right? I can write this as mx double dot plus kp. I'm just bringing it to the other side of the equation. X minus x desired equal to 0. So what is this? This is the error, right? So you have an error multiplied by the gain. What does this remind you of from the PID control? This is the P control, right? The P part of it. So we created so this is the controller. We created this from the behavioral system, and these two together now looks like mass cross a fixed spring, right? So you see the difference. Then just write out your PID controller. But we need to understand what our system behaves, then we can design our controller for it. So you have the P controller, this is dynamic of your system. So now if you want to solve, so you can easily solve this. Use OD45, you can solve and see the behavior of your system. This is, you can see this controlled or not. It's not. You'll see that you might have overshoot because you keep going back and forth, right? If it's not properly tuned. So this is your position gain. For P. All right, so now how to fix this? So far we have my water bottle that hasn't been emptied. I took water, water, drinking it, and I love water. Not taste like anything. So here, I have a prismatic joint, right? And I need to stop at some specific x of d. I created a controller, of force, an input that I know I have to pull, right? It goes back and forth. Maybe it starts doing this very close, but does not stop. So I need to create another expression and make sure this will stop. Right? Makes sense? So you are able to move it. You're able to be very close around where you want to be, but you might be able to. Sometimes just tuning this, you might be able to stop. But in case you didn't, you need another expression. Do I have a page after this? No, I'm going to create a page. So sorry, you also have to do that. Add a page. View seamless so you can see what's going on here. All right. So the system is stable. Assuming we can find this equal to 0, but might be oscillatory. Oscillatory. I hope that I wrote it right. So oscillatory is like this. This is stable because this is bounded, but it does not stop. It does. So that you have a steady state error that might be larger than what you wanted, right? You want to get rid of that part. Now, to do that, we can define another function, right? The same, we can use a potential field again, and then define another function to get there. So I'm gonna say my potential goal, I'm just calling goal, like the x sub v that I wanna go to, desired, is gonna look like 1/2 kp, which I had, x minus x of goal, transpose x minus x of goal. So this is a vector, just putting in vector form. So we can write the dynamic of our system using the Lagrangian, right? I'm just gonna write that. d dt, okay, x dot, because that's my only variable, minus partial of k with respect to x is going to be F. This is my force, the internal force. Our F is V goal, Vx. This basically I'm using potential field, so this is my potential energy. Now, if I put this back in here, d dt, k, x dot minus, since both of them are with respect to x, I can bring them in the same partial differential and put in the parentheses equal to 0. So if I can find a function that makes this 0, this is going to be stable. Now, to achieve asymptotically stable, when you reach actually asymptotically get to the position that you want, your x desired. I don't know why I go there, but to achieve asymptotic stable, what do we have to do? Stability. Let's say when the prismatic joint is moving, it has a velocity, right? How do you stop something from moving? What has to be 0? The velocity, right? The position changes, but once your velocity is 0, it means that you stop. So if I have a velocity vector, because I'm trying to define something that makes sure that my system stops where it's supposed to. So I can create or artificially create a force that opposes the velocity. Make sense? So let's say there is a force Fs that opposes the velocity, right? I put it in a random direction because I don't know where my x dot is. So any direction, a force that's opposed to that, and make sure that, so once the two are equal in opposite direction, then there will be 0. So I'm defining this. Instead of f of s, I'm just gonna fs. So fs transpose x dot is to be less than 0 when x dot is not 0. So fs, I can define negative kv x dot when kv is positive. Basically, whatever x dot is, I'm making sure that I'm scaling it in a negative direction, so it will stop. Does that make sense? I'm pulling something in a direction with some, let's say 2 meters per second, right? To oppose it from stopping, you have to pull in the opposite direction with the same value, right? So this will help if x dot changes, you can tune this to match. That's why we have this coefficient here. Just calling it k velocity, kv. Now, to achieve asymptotic stability, the dynamic of my system that I'm using just the Lagrange formula because I'm dealing with potential energies here, so it looks easier, should be equal to this Fs, right? So the dynamic of your system, if this is equal to F external, equal in opposite direction, you will stop. So this bottle will stop at the point that you expected it. Now let's write this down and see what we get. Do you remember what was the first law we found for proportional part? What was the first force? So we are solving the same problem, right? This is solving this. So we found a position control. If I start from any position and want to go toward the desired, I have to have a force that moves the object in the direction that I'm expecting, right? So here, this was our control law, right? So my F would be negative Kp x minus x goal or x desired minus some Kv times the velocity. If I apply this force, this fake artificial force that I created to the dynamic of my system, which was mx double dot. So if you solve this for that prismatic, is mx double dot. We can find it from Newton law that I did. We can also find it from this. You will get mx double dot. So you basically have mx double dot equal to fs. So if you write it, is mx double dot equal to negative kp x minus x goal minus kv x dot. Now if I rearrange mx double dot plus kv x dot plus kp x minus x desired or x goal equal to 0. If I can solve this, the system is stable, you're going to stop where I want it. So this is your control law. We implemented this as an artificial part of our dynamic of our system. What does this look like? We saw at the beginning before I start. The general mass spring system equation, right? Can we solve this? Yes. Second order system, we can. So when we solve this, what does it mean? We made the system to look like a complete second order system. Now we can look at the response. If the response look like something, so if we wanted to get x desired, right? That's the goal. So I'm going to look at the response. If I got this, I'm not tuned. I have to change Kp and Kv. But if I got maybe something like that, or even better, if I got this, is under, but still good. My system is controlled, right? Then you have to check the specification. What was the rise time expected, or what was the settling time expected of the system? How fast, basically, your system reaches the point you need. So now by looking at the response, so now we can tune these two values. We are discussing only one joint right now, right? I will show you what to do when you have multiple joints, but right now we have one joint. So now plot that, see the response, you like it, good, not, tune until you get this. How to tune those? There are different ways. Then algorithm, adaptive methods, you can use MATLAB tuning toolbox, you can create a system in a Simulink, right? So there are different ways of tuning, but you build the dynamic. The dynamic is complete now. So remember, this part is the fake part we added. It didn't exist in our system. So we created the derivative part because it's related to the velocity, right? So position gain, velocity gain. Now this looks like a system. You can find the frequency, right? The frequency and damping ratio and the frequency for the closed loop. So why we say closed loop? Because we added the controller to the system, we are reading feedback that you have error in the system, right? So this is an equation for a closed loop system. What is our open loop system here? So we ended up getting this equation, right? I just did that over there. I say this is a closed loop system. You agree with me? What is the open loop system for this? It's just a mass. It's just a mass and prismatic, right? There was no feedback, nothing. We created that. So we basically had our plant, right? And then we put, well, we have a controller here, controller. We are reading, this is X desired. We are reading the error here, right? X minus X desired. We keep putting it in the system. So we created a closed loop that has feedback. Now we can define damping ratio and frequency for the system. So hopefully you know how to find them, but if not, if we divide everything by M, we have Kp over M, X minus X desired plus Kv over M. So this is omega squared. We can also write zeta, I actually have it here. Zeta is Kv over 2 squared of Kpm. Hence you have 2 omega, 2 zeta omega. This is a general formula how you write a second order system, right? X double dot plus 2 zeta omega X, or here the error, plus omega squared X dot. So that's a second order system. So, but the difference is this damping ratio is the damping ratio of our closed loop. So you have Kv and Kp here. These are your controllers, right? So if I ask you to find the damping ratio of the open loop system, these two are 0. Our system doesn't have damping, right? Because it's just the mass that you're moving. But if it had, if there was a spring and damper in the system itself, the open loop damping ratio and frequency are different from the closed loop. The closed loop includes your controller. So if your system, your control system requires to have a specific frequency or damping ratio, that's how you find it. Why the frequency of a control system is important? Why do you want to check that? You're controlling a DC motor, let's say, right? Why it is important to check the frequency after you're controlling it? Kp over M creates the frequency of the system, right? So what do you think is important for us to check this? What could happen? Because we are tuning the controller, right?
If you end up overclocking the motor.
So usually you can tune Kp, only use the P controller, and then pick a very large Kp, right? Create a very large damping, frequency. It might break your motor, right? If it's equal to the natural frequency of the motor, what's going to happen? Also same for here. So when you're tuning, you want to look at these values. You don't want to overload your motor. You don't want to, your controller should not break your motor, right? So that's why we have to look at the closed loop frequency and damping ratio. The damping ratio is mostly about how the controller behaves. But this is also for the structural integrity, making sure we are not breaking our motor. So when I say motor, it doesn't have to be rotational. It can be linear actuator as well. It's going to be linear actuator or rotary, or could be pneumatic. So when we're talking about actuator, I'm talking about all of them. Yeah, I just use DC motor because it's easier. Yes.
What do you know about the motor method?
Well, you must look at the data sheet. I don't know. They will have the information for you. You also, it's not just the natural the frequency of your, so this is the frequency of your system, right? You also will look at the structure of your system. What's the natural frequency of the system? Right, of the arm that is moving with it. So these are that you will probably tell your structural engineer, hey, reinforce it. You know, if you have to use that, you know, if you have to use that controller. All right, so I think we're kind of running out of time. Let me see how far we got. Game selection. So that's the part that we will tune. Okay, I'll leave that for Friday. Password, yes. I'll leave that for Friday. So today we finished up to here. So this is a PD controller. We are gonna stick with PD controller for our robot. Because the I part, if you add, you need to make some changes, so we're not gonna get there. I'm going to end this session here so I can give